Okay, is that better? Can y'all hear me now?
Yes, we can hear you now.
Oh, I'm so sorry. I'm so sorry. Okay, well, we will start over again. Let's see, let's get back to where I was. Where do I want to be here? I want to be here. Okay, so we'll go back. I had said earlier, but I guess y'all couldn't hear it except for the three in the room. I entered 2 answers incorrectly on the test. And also there's 1 question that doesn't have enough information. So everybody's getting credit on that one. We'll see it here in a minute. And then I'm going to go over the test and show the correct answers. And then if you will just send me an email, just initiate an email string to me and just send me an email and just say like grade ? And I will send you back. I've got the official grades in an Excel sheet. And I went back and because I couldn't get iLearn to regrade the attempts. There's probably a way, but iLearn is just incredibly complex. So the grade displayed in iLearn is probably not correct for you. Most people didn't get hurt much, if at all. Most people actually improved. Several people improved markedly. But I will be glad to email back and forth with you individually because I don't really know how else to do it. Okay, so on this first one, we're just using the affinity laws to recast this pump. When recasting the pump curve from 1750 RPM to the measured speed of 1790 for the point 200 GPM and 103 feet of head, the flow becomes, and I have this little Excel sheet that shows the calculation for number 1. It's just the ratio of 1790 divided by 1750 times 200, which is 204.6. And so then I checked the 205 box, which is closest to it. And then for the feet of head, you just take that ratio and square it and times the original head. So 1790 over 1750 squared times 1.03 is 107.8. And so I guess that would be 108 feet. And so that takes just that 1 point and recast it up here. And then of course you would have to recast a whole bunch of points and draw a smooth line through it to have your pump curve at a different speed. Okay, so question 3, this was actually kind of a booger bear to calculate. You could do it in measure, but anyway, you have this system with all this detail, and this is the pump operating at 1790. Suction gauge 3 foot above the floor, discharge gauge 6 foot. Sum of suction side loss coefficients between the suction gauge and the pump is 2.1. On the discharge side, the sum of the loss coefficients is 1.7. All suction side piping and fitting are 4-inch. On discharge size, it's 3-inch. The flow is 200 GPM. Suction side tank has gas overpressure of 5 PSIG, and discharge side tank has overpressure of 15. And then I've given you gauge pressures across the pump. And so I ask you on this one to calculate the pump head. Well, now if you realized you could do this in measure or PSAT, but of course not everybody had access to that, but you can calculate it. And but this is the string of calculations it takes to get through this. But I think it's certainly worth looking at this. So you start out 200 GPM, and you have to convert that to cubic feet, and it's 7.4805 gallons per cubic foot. And so that comes out 26.736 cubic feet per minute. And we really want to work in seconds. And so you divide by 60 and you get 4456 cubic feet per second. So that's just the flow rate recast to different units. Then we need the cross-sectional areas on the suction and discharge. So, you know, the 4-inch is pi d squared over 4, 0.08727 square feet. And at 3-inch, it's 0.04909 square feet on the discharge area. And then you can take this volume flow rate and divide by cross-sectional area, and that gives you the average velocity. And so in the 4-inch pipe, we're 5.106 feet per second. And then you can take that v squared over 2g, that's the velocity head. And so v squared over 2g, that's just gravitational constant. And so I didn't write all the units on this one, but it comes out in just feet. So in the 4-inch pipe, velocity head is 0.4052 feet. And in the 3-inch pipe, same arithmetic, just change the number. This is the cross-sectional area at 3 inches. So we've got 9.0778 feet per second. And then that squared divided by 2g is 1.2806 feet. So those are the velocity heads at the two different diameters. And then for the suction side losses, we take the velocity head, k times v squared over 2g, so that's 0.4052 times 2.1, 0.851 feet of head loss on the suction side between the gauge and the pump suction. On the discharge side, it's that velocity head 0.2806 times 1.7, so 2.177 feet. So those are frictional losses that we have to take into consideration. Then we have the difference in gauge elevation. The discharge gauge is 6 foot, the suction gauge is 3 foot, so that's 3 foot that the pump has to provide. And then we've got the delta pressure terms. We had 56.9 minus 15, and that's PSI, times 2.31 if it was standard water, but it's not standard water, it's 250 degree water, and so you have to divide that by the specific gravity, which is 58.82 divided by 62.37 or so. And so we get about 102.63 feet for the differential pressure term. And then you just have to add all of these up. So the difference in velocity head from this is on the discharge, this is on the suction, so the pump has to provide that. So that's that differential term here. And then here is based on the pressure difference. There's the gauge elevation, friction losses on the discharge side, and friction losses on the suction side. So on this calculation, I got 109.53, and that's feet. And I went ahead and did it in measure to check my numbers for good measure. And so I think putting in all of the information, it comes up with 109.58. So it's pretty close. A couple of conversion factors are off, you know, a little bit, but at any rate, so going back to this, then we got 109.6. So bingo. So that's this one. Okay. This problem is not really workable because it's supposed to show 40 feet of elevation between these two free surfaces. And I didn't get that on the problem. So this is the one I have thrown out. So I have given everybody credit on number 4. The idea was to have the 40 feet from there to there, but somehow when I did the diagram, I didn't get that in there. So apologies on that one. Okay, so moving along to number 5 here. Pumping system with water at just standard water, 60 degrees is at a flow measurement with one pump in operation, supplying 1,250 GPM and 175 feet ahead. Second measurement shows 3,000 GPM with a system head of 290 feet for the same system with 3 pumps in operation, so we can run parallel pumps in this. Calculate the system curve and answer the next question. Assume the exponent is 1.9. And then this is the equation. So basically, you just have to write this equation twice. One with 175 for HT is equal to HS plus K prime times Q, which is 1250 raised to the 1.9 power. And then you write it again for the second point where total head is 290 plus static, which you don't know, plus K prime, which you don't know, times 3,000 to the 1.9. And then you solve that. So let's see, you can, if you did this in measure or PSAT, and it's pretty darn easy. If not, then you have to do a little bit of math, but it's still not all that much. So here's, with these points put in, the total head is 148 is the static, and there's the flow coefficient, 0.40 is 351. And so if we go back, so 148, if you run the numbers, it's 148.1 is what I got. And then this one just asks for the K prime flow coefficient. So that's those two. 7, we got a 10 horsepower motor installed on a pump. Nameplate has the following information: 1750, 460 volts, full load amps 12.4, energy efficient rated, assumed power factor is 0.8, and motor efficiency is 0.9 or 90%. Electrical measurements were taken, and we got those voltages and currents. This pump operates all the time at this condition, and electric power is $80 a megawatt hour or 8 cents a kilowatt hour. What's the annual cost? So we simply have to average the, oops, that just shows the math on the other one. So we average the voltages and we get 482. We average the amps and we get 10. So volts, amps, square root of 3 times power factor divided by 1,000 is 6.678 kW. And then that's all the time, so it's 8760 hours per year at 8 cent electricity. So it's 4680 is the correct answer. So 4680, okay. So this is the same pump, only this time I'm asking you the shaft power delivered to the pump, and the pump and motor are direct coupled, so there's no belt loss involved. And so, well, this is the KW. Now this is input to the motor, and since the motor efficiency is 90%, we only get 90% of that out to the shaft, and then we just have to convert from KW to horsepower. So it's 8.06. Should be correct. So 8 horsepower. The pump, let's see, pump is delivering 2,500 GPM at 215 feet ahead. Fluid is motor oil with specific gravity of 0.91. Input power to the motor is measured to be 144.2 kW. Motor efficiency is 90%, power factor is 80%. What is the pump efficiency? And so let's go back and take a look. So this would be 9. So pretty simple. The the water horsepower or fluid horsepower, whatever you want to call it, but it's GPM, feet of head, times specific gravity divided by 3960. That's the energy that's showing up in this case, the oil. And so that's 123.52 horsepower converted to kW is 92.143. The brake horsepower, this is the measured power into the motor, and we're told the motor is 90% efficient. So 90% of that is actually going into the pump shaft. So that's 129.78. So the efficiencies, that ratio, are 71%. Okay, 10 industrial pumps can generally be classified into two categories: positive displacement, and the other is centrifugal. Okay. If a pump does not have the needed net positive suction head required, when it's operated, what problem would most likely occur? And that would be cavitation. Don't have enough pressure on the suction, and so we're getting to the vapor below the vapor pressure, and the fluid is boiling in the pump. In PSHA, net positive suction head available is controlled by the piping system and how the system is constructed. Okay, 13. Flow control valve has a CV equal to 495 in the 50% open position. If the pressure drop across the valve is measured to be 20 psi, what is the flow rate through the valve? The fluid is 250-degree water with a density of 58.82 pounds mass per cubic foot. The valve and piping are all the same diameter, so we don't have to mess with a geometry factor. And so on this one, pretty straightforward. Specific gravity, this is what I use for standard water, someplace 62.30 something. Got a little calculator that says 37, so that's what I used. So specific gravity, 0.943, and then Q is CV times delta P and PSI divided by specific gravity square root, and so it's 2279.6. 2279, okay. The pump in a system can be operating at peak efficiency and the system can still have potential for large energy savings. Absolutely. That big example at the end of the pump lectures was all about that. When evaluating savings from the installation of a VFD to control flow instead of using a throttling valve, the amount of static head in the system will affect potential savings. Absolutely it will. That's what that little article we went over towards the end talked about. The pump affinity laws are properly used to predict operating points for changes in pump speed or impeller diameter. No, it's used properly to recast the pump curve. So that's false. Operating a centrifugal pump close to its BEP will lead to good pump efficiency and low maintenance costs. That's true. It doesn't say system efficiency. It means that pumps love to operate right at that BEP. So that's true. Fluid entering a centrifugal pump must have a well-developed velocity profile for the pump to operate at its rated efficiency. That's true. If it's all chopped up, then there's no telling how bad it's going to be. For two identical pumps operating in series, the head developed for any specific flow rate is twice that of the single pump. That's correct. That's true. 20, if standard water flows through a throttled valve at the rate of 700 GPM and a pressure drop of 15 PSI occurs across the valve, how much energy was dropped across the valve? Well, that's 20, very simple. 700 GPM, 15 PSI converted to feet of head, standard water. Specific gravity is 1 divided by 3960. So That's the amount of energy dropped across the valve, 6.125 horsepower. 6.1, so that'll be this one. Okay. Cavitation is the formation of what inside of an operating centrifugal pump? Vapor bubbles. There are two types of sealing methods for pumps, mechanical and packing. Is this a good arrangement? No, you don't want to have this cavity up here where air can collect. So that's not good. 24. If the tank shown above is filled with motor oil, density 52.74 pounds mass per cubic foot, calculate the pressure that will be read on a gauge at the bottom of the tank in units of PSIG. Assume the tank is filled to an elevation of 35 feet and the tank is open to atmosphere at the top. And so, okay, so specific gravity is 0.846. And so 35 feet divided by 2.31, if that was standard water, that would be your answer. But this stuff is not as heavy as standard water. It's lighter, and so you're going to have less pressure. So you have to multiply that by the specific gravity, and that's 12.8. 12.8. Flow control for all frictional pumping systems is most efficiently achieved by which of the following? All frictional systems love variable speed control, VFD. Flow control for static head dominating pumping system is best achieved by which? And that's parallel pumping. Parallel pumping worked really well with static dominated systems. Okay, 27. So these are just our motor performance curves. So what? Curve A, that's efficiency. So motor efficiency. Curve B is power factor. Curve C is, that's RPM, rotational speed, motor speed. And curve D is percent full load amps, motor amps. Okay. Closed pumping systems do not have which of the following? They don't have any static head. Operating an oversized motor on a pump does not cost much additional energy because of the decrease in motor efficiency. That's true. You have to go way, way down before the efficiency drops. You can see that on those curves. The efficiency gets clear down to here before it even gets to down to 90. So it doesn't fall very quickly. Using a variable frequency drive is the only option for implementing speed control for pumping systems. No, there's magnet drives, magnetic couplings, there's gear drives, there's all kinds of other stuff out there. I'd say VFDs are probably the most common and best in general, but they're not the only. Variable is the only option, so I'll have to click the wrong one. When using the valve equation, a geometry factor must be included if the valve size is different from the pipe size into and out of the valve. That's true. 35, which of the following valve types not supposed to be used for throttling flow control? That's the old gate valve, not supposed to be. And, oops. Did I skip one? Oh, yeah. Oh, yeah. Oh, yeah, thank you. Good old number 4. Let's see. That was supposed to be the answer. See if we make 100. Right down at the bottom. Ah! I don't know. I think this thing has some of the old answers still saved in it, so whatever. But I think what I've gone over here is correct. So like I said, if you will send me an email, I will send you what I have as your corrected grade, and then we can communicate about it via email from here. Okay, enough of this. Let's get on to compressed air systems. So this is where we left off in the last lecture. There we go. Okay, so yeah, this is, okay, so this is regenerative type desiccant dryers. And these get you the really, really low dew points of air. For example, I know I did some work for Honda in Marysville, Ohio, big plant, and we looked at the compressed air system, and they had desiccant dryers all over the place. They were drying air to dew points of -80 to -100 Fahrenheit because they were painting automobiles. And they were painting, what, 1,500 cars a day? 1,500 cars a day. Now, what if your compressed air system screwed up and you painted 500 cars and had to go back and sand them down and repaint them? Would that be a major pain in the rear or what? So they were very, not very receptive to suggestions that they thought would have anything to do with the quality of their compressed air. So what these people were doing is they had refrigerated air dryers, which gets you a dew point of 36 to 38. And then they had desiccant air dryers that can go any place from -20 to -100 or -120. And so they were drying it and then they're drying it again. And so me and this buddy of mine, Greg Harrell, were in there. And we said, you know, we don't really think these refrigerated dryers are doing you much good. Your desiccant dryers, more than enough capacity. You could save $35,000, $50,000 a year by turning off the refrigerated dryers because they're just, you know, it's a little refrigeration system with a compressor and all that. And so we asked them, well, what's your spec? What's your compressed air spec for painting cars? And they all looked around and said, we don't have one. You're painting 1,500 cars a day and you don't have a spec on compressed air. Wow. They said, well, this other plant someplace else, you know, they use dew points. Their dew points like, you know, -40, which is kind of the standard number for a desiccant dryer. You know, desiccant dryer -40. Okay, that's kind of the number that you always think of first. But if you put reduced flows, then you can get it drier than that. And so each one of these big dryers had dew point monitor on it. And, you know, they watched it like a hawk because they knew if they get too much moisture, it'll screw up paint jobs. And they got a big problem. So we go around and look down the aisle. I think they had 5 or 6 or something like that. I mean, it was a big system. They go, yeah, -92, -80, -70, -87. So I go, well, you guys got some dry air now. You know, there's no disputing that. But, you know, if it's way drier than it needs to be, you're wasting money. And we talked about that surprisingly long time. And at the end of the day, they just said, hey, it's not worth $25,000 to $50,000 for us to find out whether we need to run all these dryers or not. So we documented the potential savings, we put it in our report, and they didn't do it. That's the way it works sometimes. Okay, so these guys are usually rated for 100 PSIG, and you know, this is what the dryer expects to see at the most aggressive condition. So usually rated for 100 psig, 100 degrees Fahrenheit inlet temperature, and they expect to see 100% relative humidity because that air is coming out of the aftercooler on the compressor, and so you're condensing moisture like crazy. So whatever temperature you quit cooling to, it's going to be saturated at that temperature. So if you cool it to 100, you're going to have 100% relative humidity at 100 degrees Fahrenheit coming in. But what happens is if something, say that aftercooler is not working correctly, if this goes up to 120, it's going to be saturated at 120, and there's going to be a boatload of more moisture in it. Because if you look at the amount of moisture the air can hold between 120 and 100 and 120, it can hold a bunch more. And so you have not condensed that out by cooling it that extra 20 degrees. And so that's going to put way more moisture in that dryer than it's been sized to handle, and you're going to have a problem. These desiccants use a porous desiccant bead, and these beads are different materials. I can't remember them off the top of my head. There's a bunch of them, but they have lots of little cracks and crevices and all that stuff, and the water molecules stick. It's not any sort of a solution, or there's no chemical reaction. They simply stick to the desiccant bead. And after a while, then all those cracks and crevices get saturated because we got all the water molecules hanging off there that will fit. And so then the desiccant has to be regenerated, which means you have to do something to drive off all that water that's stuck to the beads, so then you can go back and cool again. So you have two tanks. One is drawing the air, the other is being regenerated, and then they switch back and forth. Okay? So that's kind of how this works. Provides dew points of -40 or down to -100. Process, instrumentation, air, outdoor applications. If you got compressed air lines where it's going to get really, really cold, and you're afraid that you're going to freeze up, you get down below zero, and your dew point's 35, so all that moisture is going to start condensing and freezing. Could be a reason for a desiccant dryer. Consider point of use small regenerative dryers to minimize cost. If you have a large plant, a lot of times you may have just one or two applications that requires really, really dry air. The rest of it, not so much. And so you could put in large refrigerated dryers, dry all of the air to 35 dew point, and then have some point of use dryers, some small ones. Because the desiccants are going to cost you much more, or going to cost you more to operate than the refrigerated dryers. The drier you make the air, the more expensive it is. Pre-filtration and post-filtration is required. Desiccants love oil. So if you've got a lube-injected compressor, you have to put really good filters to make sure that that oil does not get to the desiccant. If it fouls it, then you get to throw your desiccant away. Oil and desiccant love each other so much. Once they come together, it's a union that you can't break. And so you throw them away into the trash bin of history, and you buy more desiccant. And then you try to fix whatever screwed up that let the oil get to the desiccant in the first place. Because on a large dryer, you could be talking $10,000, $15,000 to change the desiccant. This stuff usually will last 5 to 7 years if you take care of it. But, if you let oil vapors and oil droplets get to it, then it's not going to last at all. And also filtration from post-filtration is for desiccant fines. These little beads give off dust a little bit, and that dust will accumulate out in the system. It will get carried through the system, and if that air is going to controls or things that have small orifices and passageways in them, that dust can accumulate and clog those things. So anytime you have a desiccant dryer, you want to have good post filtration to pick up what they call the desiccant fines. And then the comment about oil that I've already made. Okay, so here's, I was trying to get that header out of there. Oh no, I'm not sure why that header won't go up. Anyway, so we have a number of different types of desiccant dryers. So this one is what we call the heatless. I call it heartless because it's pretty expensive to operate. So what happens is we're showing, let me get my marker so that it won't go away here. Arrow, visible, there we go. Okay, so we have our compression element. This is the compressor itself. We have our aftercooler. We're going to have a separator and trap to get any droplets coming out of the aftercooler. And then we have our twin towers. So the desiccant dryer is composed of both of these. So we're showing this tower is actually drying the air. And so it comes out of here. And then we have a bleed valve. And so we're going to take 15% of the rated capacity of this dryer, and we're going to bleed it back through this second tower to drive off the moisture, called regenerating. 15%. So, nominally, if this is rated for 1,000 CFM, say you've got a 200 horsepower compressor, you put a dryer rated at 1,000 CFM, what is it, say 500 CFM per horsepower. So we're going to be bleeding 150 CFM through one of these towers almost continually. 150 CFM. Well, if we are, let's say we're operating at 20 kW per 100, and I've got 150, so that's 30 kW of compressor power that I'm spending to regenerate that dryer, times, let's say 7,000 hours a year, because there are some times when it maybe doesn't bleed all the time, times, and if it's 8-cent power, that's almost $17,000 in compressor energy that we're wasting on regenerating. So we're running a 200 horsepower compressor, which would get us 1,000 CFM, but I only got 850 to put out to my plant because I'm bleeding 150 through this dryer all of the time, pretty much all the time. Wow. So that's where the expense comes in, that you had to pay for that compressed air and you basically just threw it away regenerating the tower on the desiccant dryer. So you don't want to do this. That refrigerated dryer would probably cost you $5,000–6,000 a year. So, we're talking extra $10,000 because you want minus 40 dew point air. Now, whether you need that or not is another question. Okay, so we're coming up the food chain. So we can get a more efficient dryer a little bit. We have to pay a little more. And so this one has a heating element. And so the regenerating air is heated. And of course, that heat's got to come from someplace. The typical thing is it's an electric resistant strip heater, which is expensive to operate as well. But it's probably not as bad as just using all compressed air, or the 15% of the heatless dryer. So now we're down to roughly 7%. So if we had 1,000 horsepower, what's that? I'm sorry, 1,000 CFM compressor and 1,000 CFM dryer, that would be what, 70 CFM. So 70, that's 0.7 times 20 if it was 20 kW. So that's 14 kW for the compressed air times, say, 7,000 hours times 0.08. So that's down to like $7,800, but I got to pay for the heater energy too. Now, some people take waste heat from like a boiler stack, blow down, something that you're throwing away, and pipe it over and put a heat exchanger in and heat that air with waste heat, in which case that's it. You know, you don't have to pay any more than for the 7% of the rating of the dryer. Another thing to consider, these percents are of the rating. So for example, you might have this 1000 CFM dryer and be running it with a 100 horsepower compressor. Let's say you're putting 500 CFM through this thing out of the compressor. Maybe you got two 100s that you can run them both, but you're only running one. Well, so you're putting 500 in. This guy over here is still going to vent 150 CFM. That's the percent of the rating on the dryer. So run a 100 horse compressor, 500 CFM, put into this dryer. We take 150 of it to regen the dryer. We've only got 350 to go out to the plant. Holy crud. You know, this runs into, you know, how much waste is there involved in that percentage-wise? Quite a bit. On this one, it would just be, you know, your 7% or 70 CFM out of your 500. But it's the percent of the dryer rating, not necessarily the airflow that's going through it. Okay, so this is better. This is a blower purge unit. And so now all of a sudden, we're not using any compressed air to regen Desiccant. We've got a blower, and you can see if you see one of these things, you go out and you see the twin tower. Desiccant dryers are easy to identify. You see these big twin towers. You see these twin towers and you go, that's probably a Desiccant dryer. Go over there, look around on the back side of it. If you see a blower sitting there, you go, oh, this is a blower purge unit. If there's no blower, you go, well, it's not blower purge. And you look and see if it's got some sort of a heating element. If it's got a heating element, no blower, then it's heated. And if it doesn't have much at all besides the twin tanks and some piping and some valves, then it's heatless. And then you're in the 15% vent rate. So they're really not too hard to identify once you get used to, once you've seen a couple of them. So this would be, so far, this would be more efficient because I just take ambient air around from the plant, blow it through the heater, heat it up, and blow it through the tower. So I gotta run the blower, but that blower is not producing any kind of pressure like that air compressor. I mean, you got maybe 2 or 3 or 4 or 5 PSI coming out of that, as opposed to 100 PSI or so on the compressor. So that's a pretty good option. Okay, and then the best is the heated compression dryer. And that's what it says up there, except I can't see it for the banner on this thing. I'm not sure how to, I don't know how to make this go away. So if I do that, it just goes to the next slide. I don't know.
I think if you click the more and then click on the chat, it'll show that you read the chat and then it'll go away.
Oh, you think it's big? I see. Thank you. My Zoom skills are better than my iLearn skills because they're about non-existent. Okay, so this is heated compression. Well, here, we'll go back and just so you can. There we go. So that's blower purge. That's exhaust purge or heated. I don't really like that. And that's heatless. So those are the names on those things. Okay. Heated compression. So these are relatively new. They've been out there, I would say, probably 10, 15 years, something like that. So this is the most efficient by far. And so we take compressed air out of the compression element before the aftercooler. So these things require, if you're going to buy a new heated compression dryer, you have to kind of rework your compressors because your compressor's set up to have that aftercooler right after the compressor. Most people that have these bought a new compressor dryer package and it all came together constructed as one unit. But this is how the flow goes. So we come out of the compression element and the note is we got to have 250 degrees at least. And then you put that air, and that air is full of moisture. You know, it hadn't dried a bit. That's just all the moisture that came into the compressor is still in that air. And you put that into the regen tower. And if it's hot enough, it can still strip the moisture out of the saturated tower. So then coming out of that regen tower, oh my goodness, you have got moisture on top of moisture. You got all the moisture that went in the compressor, all the moisture that got stripped out of the regen tower, and then we go into the aftercooler. Wow, that aftercooler is seeing quite a moisture load at that point. So you put your cooling water, maybe cooling tower water, whatever through here, and condense the bejeebers out of that moisture. And you got a separator and a trap. And then you put it all through the drying tower, and the Desiccant, this tower strips out all the moisture down to, you know, your minus 40 or whatever dew point you're getting out of this thing. So there's no waste, there's no extra blowers, there's no extra heat input. You simply use the heat of compression on the air compressor as the temperature source to regen your tower. Okay. Now, the only parasitic aspect of this at all is that your compressed air has to go through both towers. So there is a pressure drop across this tower and then through these components, and then you have, so all of the airflow goes through both towers. And that's a little bit of a parasitic loss. But as far as operating costs, these are by far the best. Okay, and I've got a bunch of slides here. I don't know, that go into various amounts of detail. I'm not sure we're going to go through all of this, but you can read through here. I mean, this is showing what the heat of compression out of the compression element into the regenerating tower. Then we've got, there's your aftercooler. We're showing there's your moisture separator bringing out. And then we go through the drying tower. And then we have another after filter for the Desiccant fines and all that stuff. And then we go out to the system. So I think we'll move on here. I think we pretty much, let's see if there's anything here we really haven't said. Using the heat of compression, usually paired with an oil-free compressor. Desiccant dryers, you know, and your best oil-free compressor is for big systems is your centrifugal. So you would typically see this with a centrifugal type compressor. Bypass the aftercooler, you know, you go directly into the dryer. Distance between compressor and dryer must be minimized. You know, you want all that stuff kind of constructed together. You know, if we have, you know, we do have the extra pressure loss going through both tanks, you know, so that's an issue to consider. Hydrothermal aging of the Desiccant may require a more frequent replacement because we're seeing so much more moisture load on the Desiccant, so it could wear out a little quicker. The temperature effects, yeah, because you got to have that discharge temperature to regen that spent tower. You can get dew point spikes during switching on these things, and manufacturers have come up with various control modifications to try to avoid these spikes. I'm not going to go through all this. Y'all can look at this. I kind of went nuts on these heated compression dryers, but anyway. Here's some pictures. So you see, this would probably be for, I don't know, 400, 500, 600 CFM dryer, something like that. You know, a person could stand up here, maybe a little taller than the person. And of course, they do get much larger than this and also smaller. But you see, when you see the twin tanks and there's some piping and valves, maybe some gauges, and that's it, then that's almost surely a heatless dryer. And then the heated purge, you look here and you got a bunch of hardware in between the tanks. Usually what this is going to be is electric resistance heating system to heat up that 7% before you regen. Blower purge, there's a couple of pictures I scavenged off the internet, but you see, you look over here on the skid where the dryer is located, and you see this is a blower. When you see that blower as part of the skid, you pretty well know it's a heated blower purge, and that's a little bit of a cartoon, but that shows the blower, a heating element, and then it switches back and forth between the towers. I'll say one other thing here. I don't have a slide. I probably should put a slide in on this. How you determine when to switch and regen a tower can have energy implications. The better dryers, if you buy a better control system, will sense the dew point of the air leaving the tower. And they will not switch towers until that dew point starts to creep up. It's called dew point switching. Cheaper control systems will switch on time. A standard time is like 4 hours. Every 4 hours, you switch. And say, if you can reduce the number of switching cycles, after you get this thing regenerated, it quits blowing air. It quits wasting compressed air. So if you've got a heatless cycle, but you're regenerating it every 4 hours, then it's going to be blowing air for most of that 4 hours. But let's say it's the wintertime and you don't have much moisture load. So it doesn't really need to regen. It's not spent after 4 hours in the wintertime. But if the controls are simple time controls, then it just keeps switching whether it needs to or not. It doesn't know if it's spent. Well, if you put that dew point sensing switching control in, it looks at when that dew point starts to creep up, it creeps up because the desiccant is saturated. Well, if it doesn't creep up, it doesn't regen. So it might sit there 10, 12, 14 hours without regenning. The other tank is dry and ready, but the tank that we're on is still good, so why switch them? So, and those controls are not that expensive. So that's one thing that we sometimes look at on energy studies. If they have desiccant dryers, one of the questions you want to ask is, well, how do you determine when to regenerate your cylinders? Do you do it on dew point switching or do you do it on time? And if they're doing it on time, then that's an opportunity to do a little project and save them some money. Okay. This is just some sort of give you a relative cost. Deliquescent dryers you just don't see anymore. That's an older technology. I don't know that I've ever seen those. Refrigerated standard would be ones that don't have the thermal mass, you know, like the tank and all that are not as efficient. You don't see many of those anymore. The heat recovery dryers are the ones that have that tank of glycol in there, and that it controls the refrigeration circuit independently of the amount of air that's being dried. So you see, and this is cost to dry 1,000 standard cubic feet per 1 year. And so really the top two are you usually don't see. So, you know, the heat recovery or the thermal mass refrigerated dryer about 3,500. The heatless dryer purge, let's say an 11.6. I think this is 5-cent power. Exhaust purge 8,000, blower purge 7,000, and heat of compression 2,000. But hardly anybody has heat of compression dryers. Now, so if you were hired, say you went to work for a company and they said, hey, we need to buy a new compressed air system. We're building a plant. We want you to help spec out the compressed air system. So this heated compression dryer, depending on the size of the compressed air system, would be something you would want to consider, because obviously for operating cost, it's far better if you need desiccant dried air. Okay, let's look a little bit about dryers, receiver tanks. Receiver tank is a storage tank. And so we can put them in different locations. And so this is a compressor. It's a little hard to tell, but I was just grabbing images that I could find. And so we're showing coming out of the compressor, and the after cooler and all would be in here, but it's before the dryer. So here's the dryer. So we can put storage between the compressor and the dryer, and this is called wet storage, okay? Because this air has not been dried. So, you know, the benefit to this is that the air spends some time, you know, depending on how big the tank is, but the air has to flow through the tanks, out of the tanks, into the dryer, and out to the system. So it has some residence time in these tanks. Well, so it can lose heat, you know, because coming out of the compressor package, we're going to be probably 95 to 100 degrees at least. And so if we lose heat in these tanks, then we drop some moisture. Some of the moisture will condense before it gets to the dryer. And also it can pull out some compressor lubricant, could fall out if this is a lube injected compressor. So that moisture in any compressor lubricant that I can trap out of these things just makes the job of the dryer all that easier, because it's taking out stuff that normally, if these tanks weren't here, there wouldn't be time to cool this down and condense anything. That air would just run straight to the dryer, and the dryer would see the full moisture load. So this takes out a little bit of moisture and potentially some lubricant that helps the dryer. So that's kind of the point on this. Now, so this one up here is called wet storage. This is called dry storage, okay? Now, so here we don't have anything, so the dryer's seeing the full load, but I've got storage tanks downstream of the dryer. So here I'm storing dry air. And of course, if I get any large spikes in use out of these tanks, I'm going to pull dry air out to the system, which is a good thing. Back here, back here, if I get a big surge out in the system, I've got wet air stored. I can pull more air through this dryer than it can dry, in which case I'm going to get a moisture or a dew point spike out in my system, which may or may not cause problems. It depends on, you know, what the system is doing and how well it tolerates, you know, a quick dew point spike or two every once in a while. So that's kind of the good and the bad of it. I should have another slide that shows the storage tanks in both locations. So it's a good idea to have wet storage to help your dryers. It's also a good idea to have dry storage to be able to supply compressed air spikes with dry air downstream. More storage is always good. Storage never hurts you in a system. It's just the fact that you have to pay for it on the front end. But once you have it, then you should have it for a long time, because there's really no moving parts associated with it. Okay, a little bit on compressed air filters. There are filters for particulates and solids. There are coalescing filters for liquids and absorption type filters for vapors. So it depends, you know, what your system is used for and what's dangerous or potentially damaging. I mean, all systems have particulate filters, you know, but the quality and the level and all that sort of thing Depends on how sensitive you are to some of this stuff and whether or not you're trying to filter vapors or not. It just depends. Some recommendations or pointers, compressed air treatment filters, size by flow rate and pressure drop. Always pay attention to pressure drop. Pre-filters, you can remove particulates, but keep that out of the compressor. These things eventually will do damage over time. Coalescing filters remove liquid oil and oil aerosols, and absorptive filters remove oil vapors and odors. It's a big world of filters. So just some different pictures of stuff you see out there. Condensate drain traps. Okay, so all this moisture we've talked about comes into the system. If it becomes liquid, we have to somehow trap it and remove it from the system. We don't want a bunch of liquid water blowing through the compressed air piping and components. So there's different types. There's float types, which work for a while. Like it's got like a float like on the back of your toilet up and down that when it gets full, it opens, goes down. Electronic sensing solenoids open and shut. Some people manual valves, some people go around. You go in some small plants and every day somebody goes around and they have all the receiver tanks and all this stuff. It's got a hand valve and they go count to 3 or 4, close the valve. Well, you know, what an exciting way to spend your day, draining moisture out of, you know, a storage tank. And then on the electronic valves, we see a lot of cheap ones are timed cycles. I'll show you some pictures of them. There's different technologies, magnetic read, capacitance, whatever. So we got float type, reservoir, non-reservoir. So there's lots of different types of condensate drain traps out there. Okay, so avoid manual or open pipe drains. Some people will just, because, you know, if it's, you got some guy, you're paying him, you know, $15, $18 an hour, and you tell him every day, I want you to go and walk around this plant and bleed, make sure there's no moisture building up in these tanks. Well, for about the first month he does it, and then you know what he does? He comes and he cracks the valve just a little bit open. So they just sit there and psst. He doesn't have to walk around, right? There's no moisture in that tank. But he's got 15 leaks. He's done on purpose because he gets tired of walking around there. It's cold outside. I got to walk over that other building. I'll just, nobody ever goes over there. I'll just crack that valve open. Nobody will ever know. That's what happens. Timer operated drain traps. We'll see some of those. They have 2 switches on them. One says, how often do I open? And the other says, when I open, how long do I stay open? And they're just 2 different dials, and you set them. And it's a leak on purpose. And you always set the timer to be open more than it needs to make sure that you don't back up any moisture in the system. So if it needs to be open once an hour for 5 seconds, it's probably open 3 times an hour for 15 seconds. That's the way the world works. Mechanical float type drains can stick open or closed, leading to waste or reliability problems. Consider demand type drains for efficiency. So some sort of a technology that's better than a float, because floats will stick, because you know, you get dirt, debris, and all that stuff in there, and these floats stick, and you know, so it's something that you can convince yourself will be durable and continue to work. So there are some pictures. I forget the manufacturer right now. This is a really good drain trap. See, it has a reservoir, and so what happens when this thing fills up with condensate, it gets up to the top, and it's got some sort of a sensing element in there that then when the liquid gets up there, it opens, and then the pressure forces the liquid down to a lower level, and then it shuts. And it never blows. It always keeps a liquid level in at the bottom of the tank. So it never blows any compressed air. So that's why we call it a zero loss drain trap. That's what you're looking for. And you're just looking for a technology that's robust enough that it's not going to cause maintenance issues. This is kind of a stick figure of the time drain trap. Say this top knob, you could set it for, from probably 5 minutes up to 2 hours. And so that's how, whatever you set that on, so you set it on 1 hour, every hour it's going to open. And then this knob tells it how long it's going to stay open when it opens. Might be 5 seconds, 10 seconds, 20 seconds, however long you want it to blow. And then it blows moisture and compressed air until the time's up, and then it shuts. And that's what you see out there. That's one out there in the field. And of course, you get the styrofoam cups and the crap, and so that's why you want this stuff to be pretty robust, because it's, generally speaking, not just the cleanest of environments sometimes. Just some other pictures of different types of zero loss traps. That's the same picture, I think. I like that picture. Okay, here's a little example. So you can see a close-up. So this guy is set for when it opens, it's going to stay open 10 seconds. Which is the maximum for this one. And it's going to open every, which one? And I guess I read it. You got to be a little careful what direction the 0 point. I think it's pointing towards the 15. So it looked to me like this thing was set to open every 15 minutes and blow for 10 seconds. Okay. So, well, okay. So let's run some numbers on this. And then you got to figure out what's the trap size. Is this equivalent to a 1/4 inch leak, or a 3/8 or a half or whatever? And then we got a leak table we can go to that'll tell us when that thing's open, it's blowing roughly, 75 CFM, whatever. And then you multiply it out and see how much air that you're wasting for a year. Okay, so one determines how often the trap opens, every 15 minutes. The other sets the time the trap stays open. So in 1 year, there are 35,040 15-minute periods. So that means each time it opens, it's open for 10 seconds. So that's about 350,000 seconds a year that thing's open, blowing compressed air. Or 40 minutes, or 97.33 hours. Holy moly, that is just a blown away. The air is worth about $400 a year. Okay, I didn't put a flow rate on here, so I can't go back and check my numbers. A zero loss trap costs $1,000, and there's all kinds of different prices. I've seen them as low as $400. I've seen them as high as $1,500. So, so I picked $1,000. So that would say there's a 2.5-year payback to replace this with a zero loss trap. It's a pretty common thing to see. Okay, this is great. This is Ford Motor Company. See the Ford on the pickup truck? Dearborn, Michigan. I was up there where we were doing compressed air. They're running 40,000 horsepower worth of compressors. One central compressor building. They had no dryers. I couldn't believe it. Everybody in our team just looked around. What do you mean you don't have any dryers? No dryers at the point of compression. They got pipes going everywhere. The small engine plant, the truck plant, the this plant, the that plant. I mean, literally, it's a campus. I mean, it's bigger than Tennessee Tech by far. Each plant is a large, assembly line kind of thing. Compressed air going all over the place. No dryers at the point of compression. So what they did, they distributed wet air. This is Dearborn, Michigan. Last time I checked, Michigan gets kind of cold in the wintertime. They'd have pipes freeze. They had all kinds of problems. Well, this was summertime. We're up there. And so we're in there. We were there for 4 or 5 days. Like the second, third day, we're sitting in there, and this guy I'm working with, he couldn't have been nicer. That was his truck. We're sitting in there talking about this stuff, and he gets a call on his radio and says, "Oh, crap. The small truck engine facility, the whole plant just went down. moisture in the compressed air lines. He said, I got to go. And I said, can I go with you? And he said, oh yeah, sure, come on. So we jumped in the truck. They're going there down these, potholes in the road and all this stuff. Pull up next to this thing. And he goes up there saying, can you see the tag on that valve? On that valve, this is the drip leg on their big, this is probably, 16-inch compressed air pipe going from central generation over to this plant, bringing all their compressed air over there. Do not close valve. They have all this moisture in the line. Well, that's what, a 2-inch valve? Now, I don't know what percent they usually had it open, but so that thing would bleed compressed air all of the time to get moisture out of the system. Well, somebody closed the valve. Somebody, who knows? Somebody's walking along saying, man, that's a waste. I'm going to close that valve and close the valve. 3 days later, the moisture builds up and floods the compressed air system, and the small truck engine facility shuts the whole plant down. This guy comes out there. He knew. He said, I know what's happened. He goes out there. He opens this valve. Look at the water rushing out of that thing. There was a puddle. I mean, that's all. That's probably half of the puddle. In some places, that puddle is like 6 inches deep. That was a big old pothole, and the water was still gushing out of that thing. We stood there for like 5 minutes, and what happens if you don't dry your air? We couldn't believe it. We wrote up a recommendation for $2 million worth of Desiccant dryers to put in their compressed air plant. Did they do it? I doubt it. But not only that, but you've got water, you've got corrosion. I mean, those pipes are going to corrode from the inside like crazy. You got rust, all that compressed air blowing by there, going to pull those particulates out. And anything that air goes to that can get clogged or plugged up, it's just a maintenance nightmare. Who in the world designed that the way it was? I don't know. But it was a mess. I mean, even if you don't want to do Desiccant, do refrigerated, at least knock it down some. But no, what they did is they put point of use out in the buildings where they use the compressed air. If they needed dry air, they would buy little small dryers and dry them right there. So they had hundreds and hundreds of these things that they had to maintain, which was another pain in the rear. And it was just not the right way to do this. I know you got it. Distribution. That looks like a perfect time to stop, doesn't it? Okay. So, okay, we're not going to meet in class anymore because I'm just a little concerned with people coming back from Thanksgiving, and we've only got 2 more classes. So I will post the remaining 2 lectures. The final will be just compressed air. We're not going to do the reading quiz on compressed air. We'll just roll that into the final. So you have 1 more grade from that. Homework, if you have submitted homework, I just look, I basically give people 100 if they submit anything reasonable. So I'll look at it, but so long as you've been submitting homework, you shouldn't have any worries about homework grades. And this pump test, I think I have the grades sorted out pretty well. And if you will email me, I will correspond with you about it. So I hope everybody has a great Thanksgiving. Be safe, stay well, and we will be in touch.